And I'm going to go here. Okay. Okay, so we'll start off with assignment number 2. I just want to be able to annotate certain things. And okay, so hopefully you guys are starting to get the hang of what we're doing here. Okay, so here what we had basically this the plan view of a building. Okay, and of course these dimensions I put here are, you know, something that I just came up with. And basically what we're asked to do was to calculate the snow loads on the upper and lower roof of the building, okay, according to the recommendation of the National Building Code. This building is located in an unexposed area in Montjoly. I don't know if you guys know where Montjoly is, but it's a very nice part of Quebec if you ever go up there, or down there, I should say, and show all the results on a diagram, okay? The importance factor is normal. So in other words, this would be a regular warehouse, or it can be anything but a school or a hospital or whatever. So therefore, by having normal, we know that the importance factor is going to be what's going to dictate one of the variables in calculating the snow loads. And of course, if you look at the cross section, if you remember, I give you here the height of the parapet. Okay, the height of this parapet is totally irrelevant for your calculations. The one that's really relevant is only the one on the upper roof. So I gave you both here. Now, like what I always do, guys, you always start with the upper roof, okay, because that's the one that has the uniform load and so on. So the upper roof, and like I said, I tend to simply, you know, I put the equation in front of me, and therefore I start worrying about all the variables I have to go look for in order to find the value of the snow load. And of course, here, I didn't bring up the table, but the importance factor for a normal building is 1.0. And of course, for a school and so on, it becomes 1.15. And for post-disaster, it's 1.25. Now, the SS and the SR, well, that are given to you on the, you know, the data, the climate and seismic information. And this, I find this in the National Building Code. So if we go there, and like I said, I think I only gave you 3 pages, but if you ever buy the code, you will have them from British Columbia all the way to Newfoundland, and you'll have all the major cities in each province, just like you see here in Quebec. So we said it was Montjoly. So basically what we want to do is, okay, now guys, I do suggest, okay, whenever you go to a table, you know, and I do this myself, okay, I either highlight, or I take one of these things here. I don't know if you guys can see it. Okay, I take one of these things here and I put it across the table so I don't accidentally go take the wrong value. In other words, here's Montjoly. I always put my ruler across the table here like this. And of course, then I come down and I make sure I take the right values, okay? So this way, because it's so easy for you to come across and take 3.7, and even worse if you all of a sudden take 0.24, I'm sorry, 0.26. So you'd be totally wrong here. Okay, this one's fairly close, so it wouldn't be that bad. But still, be very careful, okay? And I've seen this done in the past, not only in this table, but also in other tables where students thought that they were taking one value and then their fingers accidentally slipped down and they took the wrong value. So, you know, in school, it's going to cost you a few marks. In real life, it can be very, very serious. Okay, so be careful. Always double check the values you extrapolate from the table. So here we know that the SS value in KPA is 4.0 and the SR value is 0.4. So now I'm just going to, so I get that straight from the table, and 0.4. Now, the CB value, like I said, you have to check the characteristic length of the building, okay? And this is the equation for the characteristic length. In other words, it's 2 times the width. In other words, the smaller dimension of the building divided by the longer dimension of the building. And in this case here, it's 2 times 15 minus 15 squared. And therefore, as soon as it's less than 70, then you know that the CB value is 0.8. So ZB value is always greater than or equal to 0.8. It's never less than 0.8. So if you happen to get something here because you accidentally forgot that it's got to be greater than 70, and you put in that equation, it won't make sense. It has to be at least 0.8. And of course, the CW, like I told you, this is a normal building. There are other values, but don't bother taking the sweeping effect, because you have to guarantee that that sweeping effect or that wind effect blowing the snow off the roof is going to be there within the life expectancy of the building, and that has to be there for at least 60 to 70 years under that condition. And all of a sudden, the condition can change, and you would be responsible. So I strongly recommend that you always use 1.0. And then as far as the slope factor is, well, you got a flat roof. Well, a flat roof, there's no slope, and therefore the CS value is 1.0. And in this case here, there are no obstructions on the roof that will cause the snow to shape other than a uniform layer, and therefore you don't have to worry about any accumulation. Therefore, the CA value is 1.0. And of course, the SR value, we got that straight from the table. And now we've got all our values, and we end up getting a snow load of 3.6 kPa. And of course, as I said before, so in other words, as long as this factor here, the CB factor is the same on the lower roof as it is on the upper roof, hopefully, if it is, then what's going to happen is that, in other words, here's our building, there's our building. So in theory, if the CB value for the lower roof is the same as the upper roof, then as far as the snow load goes, I would have the same uniform snow load on both roofs. And that's what happens. So in other words, here I have the same value as here. Now, here, because the CA value here is going to change. Why? Because of the snow drifting off and having a different shape here, okay? And therefore, because of the situation, then within a certain distance here away from here, we will worry about how much more snow load can accumulate on your roof because of snow drifting off this roof onto that roof, okay? And like we said, and so in other words, if this roof was here, and if there's at least 5 meters in between the two roofs, if there's more than 5 meters, five meters or more, then you don't have to worry about the drift here. It's going to fall between the buildings, and therefore this roof and this roof would have the same snow load. Okay, just repeating what we did last week, so it's a little bit clearer in your mind. So now that I've worried about the upper roof, I start worrying about the lower roof. Now, like I said, as far as the lower roof goes, I do the same thing. It's the same importance factor, and of course, it's the same SS value for the lower roof as it is for the upper roof. The SR value is the same. Now, as far as this is what I'm saying, this is to check the characteristic length of the lower roof is still less than 70. Therefore, CB is 0.8. Fantastic. So the lower roof will have a uniform load, just like the upper roof, the same values because the CB is the same. The only difference is, the only difference is that now I have to look at how the snow is going to accumulate right at the point where the lower roof meets the upper roof. In other words, right there, how much is that shape or how much of that accumulation is going to happen at that spot? And that's what the CAO means. In other words, what they're doing here is they're telling you, this is my upper roof, this is my lower roof. And what they're saying that, and then they call this XD, okay? So here what they're saying is that, what is the CAO when X is equal to 0? In other words, this is where X is equal to 0. And therefore, what is going to be the CA value where X is equal to 0? And that's how they put it in formula form. And then you're going to want to be able to calculate the value there. That's what this CA is going to give you. It's going to give you how to calculate the value of the snow up there. And then, of course, you will go and calculate the actual XD value here. And then you'll be able to assume that it's going to be linear up to that point there. And then after that, it becomes the same uniform load here as you have up here, okay? And that's what this factor does. It tells you what is the value right where the lower roof meets the upper roof, okay? Clear? Guys, jump in at any time if it's not clear, please. Okay, let me know. Now, here you've got two equations. One is where the step gets filled in. The other one is where the step doesn't get filled in. That's why you have two equations, because sometimes you can have a very low step and the whole step gets filled in. And then this one will govern. And then when you have a high step, this is the one that's going to govern. But you have to check both. I never know. I do both. So I don't know. I do both. So here I have CA at 0, which is the unit weight of snow times the height. And the height is from the top of the parapet of the upper roof to the level of the roof, not from parapet to parapet, from parapet to the level of the roof. That's what H is. And of course, CB is the CB, excuse me, of the lower roof, and it's the same as the upper roof in this case, and the SS, of course, is the same. So I do this, and I end up getting a value of 3.1. Okay, so in other words, that's how much snow can accumulate at that point there. So that's one side, and then the other one would be where you go F for the lower roof. Okay, so F shall be taken as the greater of now. Okay, so the greater of either 2. So in other words, you can't go less than 2, or this equation here. And then of course, this equation here is that you have the unit weight of snow, you have the characteristic length of the upper roof, because that's the snow that's blowing onto the lower roof. Okay, and then of course the SS is the same, the unit weight of snow, and then the height of the parapet, and this is the CB of the lower roof. Okay, so you put in all the values, and guys, be very careful, because this value you're going to use it again to do other calculation if it's the one that governs. So be very careful that you like do what's in the brackets and then square what you have to square, and so on and so on. This is where I find most people make their mistakes when they're doing their tests, and in real life, this is where, if anything, this is where the mistake. When I do this calculation, I do it once. I store it in my calculator. I do it again, and then if they both come out to the same answer, I go on. If I don't, I try to see which one of the two is correct. I do it 3 times. So always, guys, it doesn't hurt to calculate twice and then move on, especially when the value is going to be used again somewhere else in your calculations. You should always double check. Okay. So that's, and then in this case here, I get F is equal to 2.1. Did everybody else, like I said, everybody okay with this value? Did somebody not get the value 2.1? Don't be like, now's the time. Okay. Okay, so like I said, the unit weight of snow, you take it to be 3 kilonewtons per cubic meter. That's, a realistic average unit weight of snow. But like I said, real snow is going to weigh much less than that, and it sometimes can even weigh a little bit more. So there's my F value, and of course it's greater than 2.1, therefore I will use this value here. And in this case here, I divide it, and so therefore I take the lesser of, and therefore this is the one that's going to govern the shape or the accumulation at where the upper roof meets the lower roof, 2.63. Now, I put that into my equation. So what this equation is going to do is it's going to tell me right at that point where the upper roof meets the lower roof, well, that's going to be how much snow can build up there over the winter. And then I'm saying that's, and like over the winter, it can be even higher than that, but that's going to be like, and now I end up getting 8.82, okay? kPa. Like, I'm sorry guys, I'm old school. Okay, for me 8.82 kPa doesn't mean very much, but when I see 184 pounds per square foot I've been doing everything in imperial, I get a better feeling of how much load this is compared to this. That's why I like to convert this all the time. So I convert these into PSFs, pounds per square foot. And of course, now that I've calculated, okay, now, so basically what I've done is, okay, I said, okay, here's my upper roof. Here's my lower roof, okay? All I've done now is here's my snow I've calculated here. And of course I have the same load here, but the difference is that right at this point here, the load has gone from, what was it, 3.6 kPa, it's gone all the way up to 8.82 kPa. So that would be the amount of snow I would get up here. Now all I got to do is try to figure out, well, what will be the length of the drift? Okay, and that's the XD value, okay? And that's what I'm doing. So now the XD value is the lesser of, so this is where the step gets filled in, and this is where the step doesn't get filled in, okay? So anyways, you do both. So I get an XD of 11.2 meters, or I get an XD of 8.7 meters. So therefore, they're saying that you should assume that it's going to drift over a length of 8.7 meters. And of course, you know, guys, keep in mind, okay, keep in mind, I want to make sure you guys understand this. Like, for example, if I had an upper roof here, okay, and I had a lower roof here of 5 meters, right? What would I do then? If it drifts over 8.7 meters, what would I do then? Does anybody have any idea? In other words, I'm saying that the snow here is going to be, we said it's going to be 8.82 kPa, and it drifts over a distance of 8.7 meters, but my building is only 5 meters long. So what do I do then?
You have to find the force for 5 meters.
Exactly. In other words, you guys, mathematically, you would have to find out what this value is based on the slope of this line, okay, and that would be the actual snow load. Fair enough? Like, you don't, like, in other words, this is no longer, this is just theoretical. So here, the snow load, you'd have to find out what, like, in other words, you take the slope of this line, right? In other words, you take, you take, and then you find out what it would be over 5 meters here, and that would be the snow load at that point there. Very good, Emmanuel, okay? So keep that in mind. So this is just like, these are just ways of, you know, giving you value so that you can. Okay, so that's it. Now in this case here, we know that our roof is more than 8.7 meters, and therefore that's the one that governs. So now that I've got all the information, I simply have to show this on a sketch, because that's what I'm going to basically either pass on to somebody else in the office who's going to be doing whatever he needs to do with this, or for myself. And therefore, so this is what I have. So I have here a snow load of 3.6 kPa on the upper roof. I also have 3.0 kPa on the lower roof, but the only difference is that right where the upper roof meets the lower roof, it goes up to as high as 8.8 kPa, and that will drift over a distance of 8.67 millimeters, okay? And that's it. So does anybody have any questions before I talk about today's lecture, or is everything good? You guys feel comfortable with this?
I just didn't understand the part where it exceeds when, yeah.
Like, you don't understand the part where it exceeds?
Yeah,
This
when it exceeds, yeah.
here?
Not here, but not here, but before that, you explain how if like
okay. Okay, Yavor, look, what I'm saying is that, see, these are the calculations I have. What happens if this building here, okay, was only 5 meters? In other words, this was the building here. This did not exist. Do you understand? Okay. So what happens is that you would do all the same calculations, right? But the only difference is that instead of going from down here to down here, you'd have to literally find, where is this point here on the slope?
yeah.
Do you know how to do that? In other words, look, you just do it by similar triangles, you understand? If this, so in other words, if I take 8.8 minus 3.6, that gives me 2, that gives me 5.2. So this is 5.2 here. Do you understand? Okay.
Yeah.
So I do 5.2 over, so I do 5.2 over 8.67, right, is equal to something over 5. If this is 5 meters, okay, and I find out what this value is here, then I add it to my 3.6, and that will be the value of my snow load. So in other words, this in reality doesn't even exist. But I still will have to, like, I can't just take it from there and go down to 3.6 like that. That would be incorrect. You understand? You'd have to still assume as if it's drifting over 8.6 meters and then find where that point is. And therefore, your snow load would end up looking like that on the other building. You follow?
Yeah.
Okay, that's what I'm saying. So like, you use the same procedure, everything as you do, And then, like I said the other day, if let's say, let me give you another situation so that you guys can relate to this a little bit more, okay? So let's say that now this building here, instead of being right up against the upper building, let's say that this building here happens to be, let's say, 2 meters away. You understand? There's a gap of 2 meters between the two buildings. In other words, here's a building, and there's a gap of 2 meters. Okay, so you would do the same calculations, and then after that, what you would do is you would go try to find what the value is here at 2 meters away from that point, and then this would be the snow load for the building. You would, and then, do you understand? So if this was 2 meters, then you'd have to do the same thing, and then mathematically you go find that point there. Okay, and that's what you do. So in other words, this building here would have exactly this snow load, like this, if it was 2 meters away. Okay, and then if this building happens to be going over 5 meters away, well, then you don't have to worry about it, because all the drift is going to fall in between the two buildings, and therefore you just have a uniform load here. Okay, so if the buildings are touching each other, well, then this is the value. If the buildings are separated up to 5 meters, then you have to worry about this snow drift. Over 5 meters, there's nothing. That all the drift is going to fall in between the buildings onto the ground. Is that clear for everybody? Sounds good? Okay. So, and like I said, guys, this is a very, very typical situation that we have, that you're going to come across in your career. And that's why I like to show you how to do this. And the worst situation is what is that, and I've seen this a number of times, and it's always caused problems, is that there's an existing building here. Okay, this building's already existing, right? And then all of a sudden, the guy comes and he wants to make an extension next to his building, and he puts up a higher building here, okay? And by doing this, he's completely changing the snow load condition that this building was built to, because this building only had this snow load. And now, in order for him to do this, he has to now reinforce this part of the building to account for the possible accumulation there. And that's where most of the problems occur. When they make extensions, adjacent existing buildings, and they're higher, and this is what happens. And then the person doesn't not want to pay this guy to go and reinforce that part of the building, and that's where the problems occur. So I'd rather you guys be aware of that, and you know what the consequence could be. If they don't, I've seen, for example, there was an existing building, 2-story building, and they went and they put a 3-story building right next to it, and then all of a sudden this 2-story building sued this guy with the 3-story building because he completely modified the structure, the snow load on his roof, and it became a very litigious matter. Okay. So I hope it's clear, and I'm going to stop sharing this. And so I'm going to go here. Oh, escape. Okay. So hold on a second. I'm just looking for the, there we go. So everybody sees the lecture on their computer? Give me a nod or yes. Okay, yeah. Great. Because sometimes I might have, okay. Good. Okay. So guys, like we said, first lecture, we did dead loads, and we did, of course, live load, occupancy loads. Then we did some snow loads. Another one of the loads that a structure can get, will be subjected to is a wind load, which is, of course, lateral loads. And, so now the nice thing about wind loads is that the National Building Code, I hope you guys can appreciate that a wind load is not static. Everybody know what I mean by a static load? Okay. In other words, it does not have a certain magnitude, and it doesn't have a certain direction. In other words, it's a very dynamic load, okay? And what they've done is that they've taken this dynamic load and they were able to transform it into a static load, because static loads are easier to use for analysis than dynamic loads, and therefore that's what's nice about this little way of calculating wind loads. And now, okay, now as far as the specified wind load, now the big capital letter W signifies wind load, for, you know, W for wind, of course. And of course, this is the equation you find in the National Building Code. The wind pressure, okay, this the wind pressure is equal to the importance factor, just like you had in snow, but now you have W because it's for wind. This is called the reference velocity, or the reference pressure, okay? And you'll see where that is. This, of course, this is an exposure factor. This is a gust factor, and this is an external pressure factor, okay? So these are all factors, and okay. So that's the equation. And now, P, the specified external pressure acting statically in a direction normal to the surface, either as a pressure taken towards the surface or as a suction directed from the surface. So what they're saying here, okay, so that you can understand this definition, okay? Hold on a second so you guys can understand this. Okay, so what's going to happen is that when we're going to look at this, okay, I want you guys to appreciate that when the wind blows in a certain direction, right? So let's say the wind is blowing this way. Okay. Well, on this side of the building, the wind is going to be pushing towards the building, right? Guess what happens on this side of the building? What do you think happens on this side of the building? Does the wind push against the building, or does the wind go away from the building?
The wind go away from the building?
Yeah, in other words, on this side, the wind blows away from the building and it causes a suction, okay? This is a suction on this side. And on this side, the wind blows towards the building, it causes a pressure. And that's why they say either a pressure directed towards the surface or a suction directed away from the surface. Guess what happens on the roof in this case? The roof wants to lift off the building, and therefore the wind is going away as a suction, and therefore the roof wants to blow away. It's going to get pulled away from the building, and therefore you have to make sure the building is tied down so that the roof doesn't blow off the building. And guys, I've been involved in matters where this poor man, he had a 2-story house, okay? He had a 2-story house, and in the middle of the night, the roof just blew off his house. He woke up in the middle of the night and there was no more roof over his house because it wasn't tied down, okay? So it does happen. And that's why these are suctions. In other words, we indicate them as being negative values, and these are pressures. We indicate them to be positive values. Okay, so that's what they mean. Pressures towards the surface or suctions directed away from the surface. And then you'll see later on that when it's a suction, they'll all have negative values, and when it's a pressure, they'll all have positive values. So that's what they're saying here. Let me just clear this. Okay, now like IW is the importance factor for wind, very, very similar for wind when it comes to designing for strength as it is for snow. And Q is called the reference velocity pressures based on the probability of being exceeded in 1 in 50 years. And this we get from the same table we got the SR and the SS. We get the same, that's the same table we use to go find the value of Q. But the only thing is that we're going to use the one that has the probability of 1 in 50 years. The value, there's 2 values there, but we're always going to be using 1 in 50. And CE is an exposure factor. Okay, so in other words, the building, if it's going to be like right next to a lake, it's going to have one exposure. If it's going to be way down into the woods, it's going to have another exposure. Okay, so there's different ways that the winds can affect the structure. So this is an exposure factor. CG is a gust factor. Does everybody know what a gust is? Did you guys ever stand outside and all of a sudden you feel the wind is blowing, and then at one point you feel the wind is even stronger? Do you ever feel that? Do you ever feel like, for example, the wind all of a sudden blows, you felt that it was blowing harder on you? Did you feel that sometimes when you're outside? Well, that's called a gust of wind, okay? So therefore, you can have, for example, the wind can be blowing at about 15 kilometers per hour. Then all of a sudden, you have these gusts that come in, they'll bring it up to 30, 40 kilometers per hour. So those are gusts. And I think in French, a gust is called an rafale. I'm not sure, guys. I would, if somebody can just, translate gusts into French and let me know if I'm using the right word. But I believe that in French, the word for gust is rafale. I think that's what it's called. And of course, CP is an external pressure coefficient. What this is that the way that they worked out all of this formula and everything else is that they have little models put in these wind tunnels. In other words, they have a big fan blowing the air through this tunnel, and then they have all these sensors on these models, and these pressures, they monitor how the wind is blowing it, and then this is how they come up with these external pressure coefficients so that they can, make sure they can take this dynamic force and convert it into a static force, and that's what the CP does, okay? So these are all the variables to calculate the wind pressure. Now we'll go through them one by one so you can, Now, the importance category for buildings are based on, this is going to be a repetition of what we did last week, but it doesn't hurt to, repetition reinforces remembering. So we have a low category, buildings that are represented same as the, and then we have a normal, and I love the way they describe this, all buildings except those that are low, high, or post-disaster, which means like you take whatever doesn't fall into this category, it doesn't fall into this category, or it doesn't fall into this category, we'll consider that to be normal. And guys, just to let you know, your house is a normal building, shopping centers, office buildings, warehouses, industrial buildings, those are all normal buildings, okay? And of course, high is like post-disaster shelters, and therefore schools and community centers. And of course, post-disaster are the ones that are the most important. And that's, of course, hospitals, police stations, fire station, radio stations, anything that has to stay up after a disaster is considered post-disaster. And therefore, okay, and of course, so here, guys, I won't talk about this very much, but whenever you're designing something, you design it for strength. In other words, you want to make sure it's strong enough, and therefore these are the importance factors. And if you notice that it's the same values here for IW as we have for snow, IS. I know I don't expect you guys to know this, but these are exactly the same values. This is serviceability is when you have to check for vibration or deflection, and that's why these numbers are slightly different. And that's I bring this in so that next year when you're doing the design, you'll start using both, one to check your strength and one to check your serviceability. That's why I show it to you here. So now that we have the IW, now, like I said, the reference velocity pressure Q, okay, you go to the appendix C, just like we did before, okay? So the same we did before, here are the, okay, so here are the wind pressures. Now be careful, okay? These are based on a probability of 1 in 10. We do not use these. Okay, we don't use these, okay? We will only use these values here. So be careful when you come to the table, you take the higher of the two, okay? Now I can bore you and tell you why they have this in the table, but I won't bore you. It's only going to confuse you. I know why they still have this. But these are where, and of course, these are the units here, kPa. So therefore, for Montreal, I like to know what Montreal is, okay? Okay, the wind pressure here in Montreal is 0.40 kPa, okay? And that means that Montreal, look at this. If you go to Montmagny, you can expect higher winds in Montmagny, okay? And of course, you can expect even higher winds up in Masson and in Matane. So this is what I get to appreciate. Look how high the winds can get up here, up north, all the way up in somewhere around, I don't know, I can't even pronounce that, so forget about, okay? So this gives you an idea. So this is really like around the, northern Quebec. So the winds get really high up there. So this is what this tells me, because this is all based on the velocity of the wind, okay? Okay. Now, guys, I want you to appreciate this, okay? is that wind pressures increase with the square of the velocity. Okay, so that means that if I have a wind that's blowing at 10 kilometers per hour, it's going to give me one pressure. Okay, if I have a wind that's blowing at 20 kilometers per hour, well, it's not going to be twice as strong. It's going to be 4 times as strong. In other words, it goes up by the square of the speed or the velocity of the wind. Okay, so this is based on the velocity squared. So it's not linear, it's quadratic. Just keep that in mind. So don't ever try to interpolate something because it is quadratic. Okay, and if you're going to interpolate, you have to use the quadratic interpolation. I'm not sure if you guys know how to do that. So that's, I just wanted to throw that in so for some general information. Where are we? Oh, yeah. So is everybody clear on this? Okay, so this is where we get the value for Q. And again, the units, and like I said, we have 2 columns, but you only use the 1 in 50 value, the higher of the 2, okay? So this is like, we went through this table last week, how they were able to put all this together. And does anybody have any questions here? This clear to everybody, I assume? Easy enough? So now, the exposure factor, okay? There's 2 ways of calculating the exposure factor, okay? For open terrain, where open terrain is level terrain with only scattered buildings, trees, and other obstacles, open waters, shorelines, okay? So this is called open terrain, right? So this is how you calculate the exposure factor, okay? It's a formula, okay? And what happens is that, do you guys have a calculator? Okay, take this formula here and put a value like, okay, let me just show you something. We might as well do this now. Okay, here is my building like this, okay? This building here is only 4 meters high. I want you to calculate the CE. Oh yeah, first of all, the H value is always in meters, okay? You're gonna see that later on. But I want you to calculate what would be the CE value for if the building is only 4 meters high. And somebody give me an answer, please.
It's around 0.8.
Okay,
Yep,
so it's around
understand
0.8. And what does this tell you guys?
Smaller than 0.9.
In other words, it has to be at least 0.9. So 0.8 would not be good. Everybody follows? Okay. Now, I want you to do the calculation again and put 6 meters as a height.
.9.
Exactly. Okay, so in other words, when you're calculating the CE value, okay, thank you, from 0, like from the ground level here, to all the way up to 6 meters, the value of CE is always 0.9. You follow? And then as you're going higher up into the air, it gets bigger and bigger and bigger. Okay? So for example, if all of a sudden I have a building here that is 20 meters high, okay, can somebody just put in 20 in here and calculate what the CE value is here?
1.15.
Okay, so 1.15. Okay, so guys, what they're saying is that as you're going higher up into the air, the wind speeds are bigger and bigger, and therefore the exposure factor becomes bigger and bigger. Okay, and that's what the CE value does. Okay, it continuously accounts for the fact that you can go higher and higher where the wind speeds keep on increasing, because what they do is they basically that data that they gather is only at sorry, 10 meters above the ground, and then they kind of came up with this way of calculating what would happen at the wind at 20 meters above the ground, 30 meters above the ground. Okay, so that's what okay, so in other words, what I want to stress here, from 0 to 6 meters is always 0.9, and it only changes if your building happens to be higher than 6 meters. So that's what I want, and this is for open terrain. Keep that in mind. Okay, so Now, H is the height. Okay, H is the height uh, above grade in meters, and I want to stress that. Okay, so when you're using this equation, in other words, what they mean by grade, where the ground is, that's grade, and H would be the height above grade, and this is in meters. Okay, so that's what they're saying. So that's your height. So that's the height. Now, this is an example of open terrain, guys. So if all of a sudden I decide to put my little building out here, that's where I want to put up my building. Well, if I wanted to calculate the winds on this building, that my CE factor would be based on this equation here. So that's what they're saying. So this is I give you an idea what open terrain means. Like there's a few scattered trees here. There's nothing really a lot that is obstructing the wind from slowing down. Okay, so that's why that's open terrain. Now, for rough terrain, okay, now here's a definition of rough. Rough terrain is suburban. Suburban means where you're living right now is suburban, okay? Urban, okay, in other words, downtown Montreal. Or wooded terrain extending upwind from the building uninterrupted for at least 1 kilometer or 10 times the building height, whichever is greater, okay? So that would be, okay, in other words, if you do have this rough terrain around you, in other words, you have other buildings, you have other trees, you have other things that will slow down the wind, that whole, like, so in other words, what they're saying here is that, and just trying to, so you guys, okay, so if this is a map, okay, this is a map, and I have a building here in the map. This is a plan view, okay? And now all of a sudden I have all kinds of buildings here and all kinds of trees and everything, okay? So what they're saying is that all these other obstacles that can slow down the wind from this house here, okay? It has to be at least 1 kilometer all around. If you don't have that, you cannot use this. You cannot consider it, okay? That's number one. Or, for example, if this building happens to be 1 kilometer high, okay, it has to be 10 times. In other words, so it all depends on the height, which is very rare that you're gonna have a very, but in other words, for a low building, you've got to make sure that all around that building, you have at least 1 kilometer of all these scattered buildings or all these obstructions that will help you to consider it to be rough terrain, whereby the wind can slow down a bit and will reduce the pressures on your building, okay? So that's what they mean here. Now, when you do have a rough terrain, okay, instead of using the other equation, you can use this equation here, okay? Except for this equation here, it has to be greater than 0.7. The other one was 0.9, 0.7. So what this means is that if you look at the equation mathematically, you see you have a 12 here, okay? And you have a H here, right? So in other words, if I put anything less than 12 in here, this value is going to be less than 0.9 mathematically. So that means that when you have a building here like this, and you're in a rough terrain, from 0 all the way up to 12 meters, the other one is up to 6 meters, and this one is up to 12 meters, okay? The CE value is going to be equal to 0.7. Okay, so that's going to be the value of CE for, in this case here. If you have a 6-story building, a 6-meter building, the CE value is still 0.7 and so on. So all they're saying here is that from 0 to 12 meters for a rough terrain, the CE value is 0.7. Okay. Now, of course, the same thing as before, the reference height is the distance from the ground level to the top of the building. Now, we'll talk about, now here they're examples of open and rough terrain. Buildings near the road should be designed for open terrain. So what they're saying here is that if this is your situation, all these buildings here, all the buildings here, because they're exposed to the wind and they don't have like scattered building on this side, these should be designed for, as with the other equation, with the okay, for open terrain. And if this house here happens to be 1 kilometer away from there, and 1 kilometer away from there, and 1 kilometer and all that, if you want that house there, it can be designed for, considered to be a rough terrain. Otherwise, the other one, all the other ones are considered open terrains. So that's what they're suggesting. Okay. So I hope you guys can see this. Okay, so this is just to give you an idea when to use rough terrain. When like if you're not sure, use open terrain. That's the safest thing. If you're absolutely sure, then you can use rough terrain, and it's going to reduce your pressures a bit. That's all it's going to do. Now, so here's another example. Sorry, here's another example of, this would be rough terrain in here. This would be rough terrain in here, but all the houses that would be around this open water, that would be open terrain. You understand? This house would be open terrain because he doesn't have at least a kilometer. Okay, so buildings located on the periphery of the lake should be all open terrain. Okay, and then the other ones should be at least a kilometer away. So this is what they mean by urban and suburban areas. And it's up to you. If you really want to be, take advantage of being in a rough terrain, I don't bother. I take everything to be in an open terrain, and I simply calculate everything with the first equation. That's me. Okay, I like to be conservative, and it won't make a big difference at the end of the day, but at least I know that I'll have, a more resistant building, even if the wind is somewhat slowed down by all these obstacles. So that's just to give you another idea, they're saying when you can use one or the other. Now this here, okay, guys, let's talk about this, okay? I want you to, now, what this is straight out of my National Building Code. This is the supplementary to the National Building Code, okay? What this is that it gives you the values. I want you to look at that, okay? The external pressure coefficient for in other words, this table here, those two variables or those two factors that we had in the equation. Remember, we had P equals I W Q C E. Well, we've seen this one, and then we had C G C P. Well, this table here will give you these two values combined. In other words, it combines the gust factor and the external pressure factor combined. Okay, so therefore, if you're looking for these two values, it's all in this table here. Okay, that's number one. I want you to understand. Is that clear to everybody what I just said? Okay, so this here in the equation comes from here. Now, that's number one. Number two, what I want you to realize is this, okay? This is load case number A. What is load case number A? Winds generally parallel to the ridge. Who doesn't know what the ridge is? Don't be shy, guys. Now's the time to ask.
Can you please explain?
Pardon?
Can you please explain what the ridge is?
Okay. See this line here in the building? That's the ridge. Everybody understands what I'm saying? So what, in other words, when you're doing your load calculation, this means that the wind, let's put, what would be a nice color for wind? That means that the wind is blowing generally perpendicular to this line here. Everybody understands what okay? So in other words, the wind direction is this way, not this way. So this table here, okay, is only good for when the wind is blowing this way. That's what this table is going to give. And then there's going to be another diagram where we're going to see when the wind is blowing the other way. But let's not worry about that right now. So that's the other thing I want you to be aware of, okay? Now, remember when you wanted to calculate your value of CE, right? It was, I don't remember what it was, but it was something like H over whatever, okay? Here, what they're trying to make you understand is that when you have a slope roof, okay, when you have a slope roof, you can take the mid-height of this gable, this is called a gable, and you can use that as your height. In other words, people say, do I take the height going right up to the ridge here? In other words, do I take this H, like here up to there? Well, you're allowed to take halfway between the ridge and the straight part here of the walls and take that to be your H. That's what they're showing you here, okay? You're allowed to do that. And what they're showing you here, let me just, okay. What they're showing you here is that these are the different surfaces that your wind is going to have a different effect on, okay? So for example, this is surface number 1, and that's what this is. This is surface number 1. And of course, this here is surface number 1 goes from here to here, okay? And what they're saying is that if I want to calculate the pressure here and I need to calculate the CP/CG value for surface number 1, if the slope of my roof is from 0 to 5 degrees, then that's what I use for the values of CG/CP. Now, you'll notice that you have 1, which is like in the middle here, and then you have 1 that's at the edge, okay? And you'll notice that at the edge, the value is always higher than in the middle, okay? So therefore, the wind tends to get stronger as it wraps around the building, okay? So therefore, this area here would have a higher wind pressure than this part of the building here, okay? So this, in other words, this is 1, and this is 1E at the edge of that surface, okay? The same thing happens here. This is my surface number 2, okay? This way, and then I have 2 along the edge. This is surface number 3, and I have 3 along the edge. And now they're showing you on the back side of the building, this is surface number 4, and I have 4 on the edge, okay? Now, what they're showing you here, okay, is, okay, what they're trying to show you here, what they're trying to make you understand is that I have positive values and I have negative values. What does that tell you? What does positive values and negative values indicate? Does anybody have any idea? Don't be afraid to give me a wrong answer. They're all correct today. Just give me an idea what you think. Why do I have a positive value here, and all of a sudden I have a negative value here?
Does that mean the positive means pressure and the negative is suction?
Exactly. That means like when the roof slope here goes from 0 to 5 degrees, when the wind is generally blowing in this direction, I will have a positive value here. I will have a pressure here, but on the roof, it would be a suction. The roof would want to blow off. In other words, it would be blowing away from it. Okay, so that's how they indicate on the positive values. Give you very good. Jimmy, you don't want to give me the answer? Sorry, okay. So in other words, here on surface 1 and 1E, when the wind is blowing generally in this direction, on this surface I have positive values, in other words, blowing towards the surface, and then on 2E as well as 3E as well as 4E, they're all negative. In other words, it's all suction. The material would want to try to blow away from the building instead of staying on the building. And what you should find interesting is that when you start looking at an angle above 30 degrees, okay, on the roof, on the windward side of the building, it starts being positive even for surface number 2, but it always stays negative for surface number 3. And then as, you know, and then of course, if you have like a perpendicular roof, 90 degrees, okay, then it ends up being totally positive for surface number 2 and negative for surface number 3, okay? So now, so this is what, okay, and now we'll talk about this. This tells you, like, there's a way of calculating, well, how much of this wall is considered to be the end zone here. I'll show you how to calculate this Y if you need to calculate it. But I want you to understand, you know, like what these values are, what the negative and the positive sign mean, and what these numbers here are. So in other words, these numbers here are these numbers here, okay? In other words, this tells you what surface that these values of CG, CP, or CP, and here they call them CP, CG, they tell you the values of those factors are for those surfaces depending on the angle of the roof, okay? So if you have a flat roof, then this is what you use. If your roof happens to be a 20-degree slope, this is what you use. If it's a 30 degree to 45 degrees, if it's 90 degrees, okay, and here it doesn't make a difference, it's about the same. So therefore, they're telling you, depending on the angle of the roof, the values for, okay, the values will change, and it's gonna have an effect on how the wind blows around the building. So does anybody have any questions? Or something not clear? Guys, don't be shy. Now's the time to ask. Is everything okay? Because I don't want to go on if you guys aren't too sure, and if you're too, don't be, don't worry about asking questions. So may I go on? Is everything clear? Thank you. Now, so like I said, this is load case number 1. Winds generally perpendicular to the ridge. Okay, so perpendicular to this line here. Now, then you have load case B, winds generally parallel to the ridge. Now, in this case here, there's only one row, but there's more surfaces. That's the problem, okay? So here, again, so this is load case B, winds generally parallel to the ridge. Okay, so in other words, the wind is blowing, they're showing you here, like the wind can be blowing anywhere between here and here, okay? And people have asked me, says, well, what happens when the wind's blowing at 45 degrees? Well, you take it to be parallel in this direction, and therefore, when the wind is generally blowing in this direction, these are the values. Now, what I find amazing when the wind is blowing parallel to the ridge, look at this. Negative, 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 negative. The only positive surfaces are 5 and 5E. In other words, the only time that the wind is pushing on the building is for this surface here and this surface here. Otherwise, everything else, the wind is trying to push everything away from the building. You understand? So everything, so when the wind is generally parallel to the ridge, everything's in suction, and it's only the side that's on the what we call the windward side that's in pressure. Everything else is negative. Like, don't you guys find that amazing? Or it doesn't fizz you in any way? Next time, guys, look, not if we're learning about wind, okay? If ever you're standing, okay, if ever you're standing, I'll tell you one thing. Let's say this is your house, okay? This is your house, let's say, and next time you're outside, let's say the wind is blowing this way, right? And if you're standing on this wall here, this is where you're standing, okay? This is you, okay? Next time you're standing there, try to be a little bit conscientious, okay? Maybe you won't feel it here because you're too low down, but next time you're standing there, you're more likely to feel the wind pressure in your back than you will feel it on your stomach. Next time you're outside, try to, and you'll see that if the wind is blowing this way and you're standing on this side of the building, and of course, if you're standing here, don't worry, you're going to feel the wind coming straight at you. So, but if you're standing here and you've got your back turned to the wall, don't be surprised if you feel more of a push on your back than you feel a pull, or you feel more of a push on your back and a pull on your stomach than being pushed against the building. In other words, you'll have a tendency to be pulled away from the building than you are being pushed towards the building. And if you, next time you're out there, mind you, the wind has to be relatively strong for you to be, feel this, but that's what you're going to actually feel. It's amazing, okay? And then again, depending on if it's parallel, well, if it's parallel, if you're standing here, you're going to feel, you're going to be wanting to be pulled away from the building. If you're standing here, you're going to be pushed towards the building. If you're standing here, you're going to be pulled away from the building. And that's how that's what you're going to feel the wind doing to you. It's going to either pull you away from the building or it's going to push you towards the building. And that's amazing. I mean, so guys, so like I said, so the load case B, okay, the values of CP, CG for that equation, you get them straight from this table. And like I said, all the surfaces are negative except for the one, okay? Now guys, just so you understand some terminology, if the wind is blowing this way, okay, this side here is called the if you ever hear this term, this is called the windward side. And this side here is called the leeward side. Okay, so you might hear this, you might read this in books and everything else. Okay, so this is the windward side and that's the leeward side. When the wind is blowing in this direction, this is the windward and this is the leeward. Okay, and so on. And then of course, if the wind's blowing in this direction, this becomes the windward. It's just like we have definitions when we're looking at water flow, you know, upstream, downstream, you know, to define like in which direction the thing is flowing when it comes to water. When it comes to wind, we tend to define which one is downstream to the wind and which one is upstream. And when you're looking at surfaces, this would be called windward and this is called leeward, windward, leeward, and so on. So if you hear those terms, that's what they're referring to. I just thought I'd throw that into for your general information. Does anybody have any questions? Now, these are little footnotes, okay, to these two diagrams, okay? These are little footnotes to these two diagrams, and we'll go through them slowly, and this way you guys can have a better, okay? Now, here, what they're saying is that the value of CPCG in load case A and B are for low-rise buildings. In other words, you can only use this if the building here, if this dimension here, H, which is the height of the building, okay, and this is the dimension ds, in other words, the plan dimension ds, okay, if this is 8 meters and this is 6 meters, yes, you can use that table. But if this is 8 meters and this happens to be 12 meters, you should not be using the table. In other words, this is only good for the ratio where the height is less than the dimension of the building. So in other words, ds is a smaller dimension in plan view. So in other words, this would become ds. And if this ds value is less than the height of your building, okay, then you can't use these tables. And of course, it has to be less than 20 meters. If you happen to exceed this, there are other formulas, okay, but this is very applicable to residential houses, very applicable to industrial buildings and so on. So, but if ever you don't meet this criteria, you should go and buy yourself the supplement. You spend another $180 and go find the other ways of calculating the wind loads, okay? But this applies to 80% of the buildings that you're going to be designing anyways. So now that's the first thing. So second thing is the values for roof loads not shown. In other words, if you happen to have an 18-degree slope roof and it's not shown there, if you want, you can interpolate. If you don't want to interpolate, I suggest you always take the higher value to give you the worst case. And I don't interpolate. I simply take the higher value and I don't interpolate. Okay, but you can interpolate linearly if you want to. Okay. Positive coefficient denotes force towards the surface. In other words, a pressure. Whereas negative coefficient denotes forces away from the surface, in other words, a suction. Okay, so that's how you can differentiate on which side is the wind pushing towards the wall, on which side the wind is pulling away from the wall. And that's the negative and the positive sides of the table give you that, tell you which way to consider the force. The reference velocity h for pressures at mid-height of the roof or 6 meters, whichever is greater, okay? So in other words, here, what they're showing you here is that if I happen to have a gable is simply a slope roof, okay? Now, if I want, I can use this here, okay? I can go and find out what this, and I can take this as being my height, okay? Now they're saying here is that this height is either going to be that height or 6 meters. Don't use anything less than 6 meters because, you know, the CE value is always the same value from 0 to 6 meters. So that's what they mean for the reference height h, okay? The mid height of the roof or 6 meters, whichever is greater. And the end zone y should be the greater of 6 meters. So in other words, minimum 6 meters to z, where z is the gable wall. Okay, z is the gable wall. In other words, okay, shown for load case number B. And then Z is a lesser of. So you've got to take 10% of the least horizontal dimension or 40% of the height or 4% of the least horizontal dimension, or 1 meter. So this, if you ever get into this calculation, you want to know what is that end zone, how far does it go from the corner? Well, this is what you have to calculate. Okay, we won't bother calculating this, okay, because we're not going to be doing any actual design. But next year, when we do the whatchamacallit, the wood and steel projects, okay, we will then be applying this to see how far is our end zone. Okay. Now, so these are all the footnotes to those two diagrams. Like I said, this is the most important one. The diagram only applies for a building that does not exceed 20 meters, or the ratio of h over the smallest dimension does not exceed 1. Keep that in mind. So, okay. Now, here, let's take all this good information and apply it to a realistic problem. Okay. In other words, here what we want to do is we want to calculate all the external wind loads acting on the school building, okay, according to recommendations on the National Building Code. Okay, the building is an open terrain, okay, located in Percé. I don't know if you guys know where Percé is, but if you ever get a chance, go out there. It's a beautiful part of the province. Okay, I've been there a couple of times, really enjoyed it. And show all your results on a sketch, which is, I will always ask you to show your results on a sketch. Okay, so here we have, okay, so in plan view, okay, we have 20 meters, we have 25 meters. We have here 8 meters. I don't know what this side here, but I have an angle of 30 degrees, so I'll be able to take some trigonometry to calculate my height here anyways. And like I said, if I look at the 20 and I know that like this does not exceed 20 meters, this will never be, so therefore I can use those figures. So I'm good to go to get the values of CG, CP, CG. So just like I did for snow, I do the same thing for wind. I always start by writing the equation. Okay, I put the equation in front of me, and then I start saying, okay, here's my equation. That's how I calculate the pressure. I need to know the importance factor. I need to know the reference velocity pressure, and so on. So let's go. So of course, this is, oops, sorry. Okay, so this is where I would come to this table here. And this table here, guys, comes straight from the National Building Code. Okay, so I have a school. We know that schools are considered high, and therefore here's the importance factor for the school, 1.15, the same value as we had for the snow. Okay, so that's where I get the 1.15. Now, I need to find the value of Q. So what I do is I go to Appendix C of my National Building Code. And of course, I go look for Percé. And of course, this is all in alphabetical order, and therefore I just got to keep going. It goes by province, and then it goes by alphabetical order. So like I said, you should give yourself a ruler. Here's Percé. So you go across with your ruler. You get to the wind velocity, and like I said, you do not use these values here at all. Okay. And here is the reference velocity for Percé. So this tells me that, man, the wind really blows at Percé. And that makes sense because it's right at the waterfront of the Gulf of St. Lawrence. So that's why it's very high. So there is the value of Q in 1 in 50, 0.85 kPa. Is everybody clear with this? Is that okay? Fair enough. And now that I've got this, let me just, okay. Now that I've got this, well, there's my 0.85. That's my Q value. Now, I know I'm in an open terrain. CE is equal to H. This is the formula that I need to calculate the CE value. And of course, it has to be at least 0.9. Okay. Now, what I can do, I'm going to have two values of CE. Okay. I'm going to have one value from 0 to 6 meters, because that's going to be one pressure. And then I'm going to have one value going up to the, call it the mid height of the gable. Okay. That's going to be from 0 to 6 meters. I have one CE value. And then after that, I'm going to have another one that goes up to 8 meters. Okay. Okay. And then, like I said, here, what I want to do is I want to try to find what the height is right here. Okay. So I'm going to have a CE value up to here. I'm going to have a CE value up to here. And then I'm going to have a CE value up to here. So I'm going to have 3 CE values. Okay. And how do I find this height here? Well, it's very simple. Okay. This is 20 meters here, right? And therefore, if I take, if I want to know this, okay, if I take 20 and I take the tan of 30 degrees and I'm divided by 2, it's going to give me the height here, okay? I mean, I'm not going to, I'm not going to get into the math part, but that's how I would be able to calculate the height there, okay? Or I take 10 meters. If you want to take half, take the tan of 30 degrees, okay, and divide it by 2, and that's going to give you the height there. And that's what I'm doing here. So I'm taking 8 degrees, tan of 10 degrees divided by 2. So therefore, and then I end up getting 10.9 degrees. And then when I put into the equation, I get 1.02. So that means that all the roof is going to have one exposure factor. The wall is going to have one exposure factor up to 6 meters, and I'm going to have another exposure factor up to 8 meters. So that means I'm going to have one wind pressure, another wind pressure, and another wind pressure, all depending on where the surface is and what it's being exposed to. Now, where do I find the values of CP and CG? Well, I simply go, okay. Now, what I like to do, okay, what I like to do is this, guys, and I suggest you do the same thing when you're doing your assignments and do the same thing when you're doing the test, okay? Set up a table, okay? This is what I do. I set up a table. This is the way I set up the table. Here, I put load case number A. I just say load case number A, winds generally perpendicular to the ridge, okay? Then what I do is I put my surfaces here. I put my surface 1, 1E, 2, 2E, 3, 3E, 4, 4E. These are my surfaces. So I know which one I'm looking at when I'm looking at my rows. The importance factor is the same for all the surfaces. Of course, the Q value, the reference velocity, is the same for all the surfaces. Now, I'm going to have one value of CE from 0 to 9 meters. Then I'm going to have another value of CE from 6 to 8 meters, and then I'm going to have one that goes from 8 to 10.9 meters. So I have 3 values of CE here. And then this here, well, what I do is I go to the table. I have a 30 degree, so therefore I take all the values that I have in this row here, okay, for surface 1, surface 1E, surface 2, surface 2E, surface 3, 3E, 4, and 4E. And that's why you see my table. I simply copy these ones here. And that's exactly what I did here. Okay, I copied these ones here. And then once I do that, I do the math. In other words, from 0 to 6 meters, it would be this value here multiplied by this value here, multiplied by this value here, multiplied by that value there. And that's how I get the pressure on surface 1 from 0 to 6 meters. And then, in other words, here's my building. Okay, here's my building, and I'm going to show you later on. Okay, so that means like if the wind is blowing this way, this is my surface number 1, and therefore up to 6 meters here, this would be wind pressure of 0.92 kPa. Then after that, this is 8 meters high here, and therefore it would go up slightly. It would go up a little bit higher, and then so on. Okay, and then what I do here, why don't I have for number 2 and number 2E, 3 and 3E? Of course, those are all on the roof. In other words, they're all higher than 8 meters, and therefore there's absolutely no value there. The only value for the roofs are the one I calculated with this value here, 1.02. That would be the values on the roof. And then for the other side, it will be very similar to the 1 and 1E for the 4 and 4E, except it's all happening on the other side. So guys, I do strongly suggest, okay? Okay, so you just make yourself a nice little table, okay? And if you look, guys, all I did here is I put my surfaces that correspond to the way that I can get the values from the other table, so I can just copy them directly here, one after the other. But if you notice here, this is IS, this is Q, this is C. This is my formula right here, okay? CP, CG. So this is my formula, and then this is equal to P, and these are all my pressures. So this is a very organized way of making sure that you get all the values correct, okay? And you're going to make sure you assign them all to the correct surfaces, and so on and so on. Is this clear to everybody what we're doing? Okay. Does anybody have any questions? Now that I've done my table in one direction, well, what do? I do exactly the same thing. This is for load case number A. Now, for load case number P, those CE values are exactly the same. In other words, from 0 to 6 meters, 0.9, from 6 to 8 meters, 0.96, and then higher up is 1.02. So the CE values are exactly the same values. I don't have to recalculate those. The only difference is now I got more surfaces. Okay, so I got surface 1, 1E, 2, 2E, 3, 3E, 4, 4E, 5, 5E, 6, 6E, okay? And then of course, this stays the same, that stays the same. And of course, here I got to be careful. Only the walls go from 0 to 6, and then only the roofs go from 1 to 2, okay? And of course, okay, so, and then after that, so I come to this table here, and I just simply take all the values I have. And here, what's nice about it is only one row of values when it's parallel to the ridge, and therefore negative, 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 negative. And like I said, only 5 and 5E, because the wind is generally blowing to this side, okay? And this is positive and positive, okay? Because here they're showing you the wind direction. It's going this way. And of course, negative and negative. So that's where I get all the values for CG, CP, CG. I keep saying CG, CP because I have the formula in my head in that order. And of course, now that I've done all my calculations, which is like, you know, like I said, very straightforward. And if you do this table, you know, like take your time to, you know, set it up. Now I'm ready to take all this information and show it on a sketch, okay? So for the sketch, very simple, okay? I simply draw a nice little cross section, okay? I draw a nice little cross section of a building. Now, what's the first thing you think I should indicate? What's the first thing I should indicate? Now, guys, this is load case A, right? So what's the first thing I should indicate? Does anybody have any idea?
The height of the house.
In other words, guys, like here, I'm going to indicate, like, for example, okay, I have surface number 1 here, and I have surface number 1 here. Which one is correct? I have surface number 4 here, and I have surface number 4 here. Which one is correct? I have surface number 2 here, and I have surface number 2 here on the roof. And I have number 3, and I have number 3. Which one is correct? Does anybody have any idea? Well, guys, just to let you know is that if the wind is blowing this way, is this surface 1 or is this surface 1?
The left-hand side.
This is surface 1 if the wind is blowing this way. So whenever you're doing a sketch, it's very important, okay? It's very important to indicate, okay, the wind direction. Okay, so you always indicate in which way so therefore, once you've indicated the wind direction, you know which is surface 1, which is surface 4, which is surface 2, which is surface 3. Because if the wind is blowing this way, this becomes surface 1. Everybody agrees? Okay. And that's why it's important to show the direction, because if I were blowing the other way, then the other side would become surface 1, and that would become surface 4, because then I know which side is in pressure, which one's a suction. Fair enough? Now, once I've established this, and I say that that's section 1, right? What do? Well, I go back to my table. I look at surface 1, and what's the pressure from 0 to 6 meters? 0.92 kPa. Okay, so on surface 1, from 0 to 9 meters, I have 0.92 kPa. So therefore, here I show up to a height of 6 meters. This is only good up to 6 meters. Now you'll notice that I put the arrows towards the wall. Is that correct?
I think so. Is
Yeah,
there any
because
problem?
the value in the table was positive. So therefore you have to show it going towards the surface. Okay, fair enough. And then you went back to look at from 6 to 8 meters, it went up to 0.99, right? That's the value that went from 0 to 6 meters. And therefore you went up to 0.99. So the wind picked up, the pressure ended up being a little bit higher when you went from 0 to 8 meters. Now I don't show the 8 meters here because I know my structure is 8 meters, okay? Now, once I've done that, right, then I move on to surface number 2. Okay, so if I go to surface number 2, now surface number 2, it only has one value. Okay, now surface number 2 is positive. So that's first thing I look up is positive. Okay, so surface number 2 is positive. So therefore, I show the arrows pointing towards the surface, and then it's got a value of 0.9 kPa. Okay, and that's how I make sure I'm okay. Now, when I go to surface number 3, well, look what happens. I go to surface number 3. Oh, I realize that I have a negative value for surface number 3. So here I'm on surface number 3. I have a negative value. Okay. Wait a second. I had a negative value for surface number 2 and a negative value for surface number 3. Oh, sorry. Hold on a second. I lost myself here.
Sorry, sir.
Yeah.
Are we in case A or case B?
We're in case A, low case A.
Okay.
But oh, that's right. This is positive. I was looking at the wrong one. Sorry. Okay. Anyways, and then you do this. Now you notice here, guys, this, I want you to be careful. Okay. Now, what I want you to do, I want you to show that the values are going away from the surface. In other words, you're showing the arrow, but here, do not put a negative sign. Okay. Because there are programs, for example, if you put this going this way and you put a negative sign, guess what the program is going to do? It's going to reverse it on you. It's going to tell you, take the opposite. So I don't want to see a negative sign here. I want to see the arrows going away from the surface. Everybody follows? Is that clear? Okay, so be careful about that. Don't put the arrow, when I'm going to be correcting your exam, okay, I'm going to be looking to see if you put the arrows in the right direction, and then I'm going to make sure that you put the right numerical value here. So the directions tell me whether it's a suction or a pressure, and that's what the arrows are telling me. So I have a pressure here, I have a pressure here, I have a suction here, and of course for number 4, I go back to here. Number 4, I have a suction, a negative value, and therefore I show the arrow going away. And then of course, that's from 0 to 6 meters. And then after that, I won't bother going back. I have another negative value. And that's how you indicate this is just for surface 1, 2, 3, 4. So that's one sketch that you have to prepare, right? Then once you've done it for 1, 2, 3, 4, right next to it or right below it, you do the same thing for 1E, 2E, 3E, 4E. And you'll notice that as far as the direction goes, they should be all the same, whether it's 1 or 1E, 2, 2E. The only difference is that the values go up, okay? In other words, you'll notice that the difference between 1 and 1E is that, okay, the values are, they should be higher along the edges than they are in the other parts of the wall, okay? And that's what you're, okay, so here you're showing the values of 1, of course, from 0 to 6 meters up to 8 meters, and then for the roof, and again, these are all suctions, these are all pressures, and these are all suctions, okay? So that would be for load case A, and then after that, you're pretty much done for load case A, and you'd have to do the same thing for load case B, Okay, so you would do the same thing. You would go back, you would do your little sketch here showing surface 1, surface 2, surface 3, surface 4. You would go back to your tables. For surface 1, you have 2 values from 0 to 6 meters, and then from 6 to 8 meters. And then, okay, for 1E and so on. So you get all your values from your table, and you would put them down. And again, you notice that in this case here, they are all going away. Okay, that means these are all in suction. Okay, so in other words, the building literally wants to literally come apart as the wind is blowing parallel. So all the surfaces that are basically parallel to the wind, it's always all in suction. Okay. Now, I want to ask you guys a question. Okay. This is something that I found interesting. Okay. The wind is blowing this way, okay, or it's blowing parallel, okay? If this is, I found this interesting, and I kind of asked myself the question. Here's my building, right? Here's my building. The wind is blowing parallel to it. In other words, it's blowing parallel to it. Why is the value on one side of the roof different from the other side? Why aren't they the same? Why is it the same here, but not for the roof? Don't you find that interesting? You see? And that's why, you know, for example, that's what they mean, that generally parallel to the roof, because the wind can change slight directions, they're not really always parallel. It will affect these surfaces differently, and that's why you have different values on the roof. Okay, and there, you know, like when the wind is blowing like this, it's high, and then in other words, this is generally parallel to roof, and that's why you have different values here. Okay, I found that interesting when I saw that the first time. I said to myself, interesting. Okay, so there you go. And that would be, of course, surface. And then you do the same thing for 1E. Okay, you do the same thing. You redo your sketch. In other words, you need, and then you put down your, and then of course, parallel to the ridge. Okay, you can't show the wind direction here because it would be perpendicular to the screen or perpendicular to your piece of paper, but you know that it's the wind parallel to the ridge. But what's important is you show the right direction of the wind, and these are all in suction. And then of course you have the one for, now here you're going to show a wind direction because here the wind is running, you know, so here you have to show a wind direction. So this way you know that this is surface number 5 and that's surface number 6. Okay, and that these values are only good up to 6 meters. And then these values here go from 6 meters all the way up to the top of your wall. Okay, and then you do the same thing for 5E and 6E. And of course here you would have to show the wind direction. And that would be basically it. Okay. Does anybody have any questions? No? Now, what I'm going to do now, okay, what I'm going to do now, I'm going to clear this, okay? So now, I'm going to take the same problem, okay, and I'm taking the same problem. The only difference here, okay, the only difference here is that I'm in a rough terrain. I'm no longer in an open terrain. I want to show you the impact it has on your wind pressures, okay? So in other words, I take the same geometry, I take the same height, I take the same angle, I take the same location, everything's the same. The only difference is that if you consider the school to be built in a very urban or suburban area and you want to consider taking that to calculate the value of CE, I want to show you the impact that has on your values, okay? So that's why I repeat example number 2. People say, aren't you doing exactly the same thing? I'm not doing the same thing. I'm doing the same project. I'm doing it in the same geographical region. I'm doing it. The only difference is that now I'm no longer in an open terrain. In other words, I'm not by the seashore. I'm going to be building somewhere where it's very wooded. There's a lot of houses, and therefore I can consider it to be a rough terrain. And therefore, I want to show you how that impacts the value of your wind pressures. Okay. So it's going to be very similar, but the only difference here, okay, everything's going to stay the same. Does anybody like tell me what would be the only difference between the first problem and the second problem? In other words, look at this equation here. Like different, like the first problem, the second problem. Would this change? Yes or no?
No.
No. Would this change? Would these values change? No. So the only thing that would change is this, okay? And therefore, that's what you'd have to worry about. And that's the only thing that would have an impact on the value of P. So therefore, okay, so here you go. Okay, so now, of course, we'd have the same importance factor. We'd have the same Q value. We'd have, now, this is the only difference. That when I want to calculate CE, okay, I would use this equation here instead of the other one. And don't forget that this has to be greater than or equal to 0.7. And therefore, here, I'm up to 0.9. I'm sorry, I take the same, I calculate the overall height, okay? And like I said, okay? And now all of a sudden I calculate and I get 0.68. So therefore I have to use at least 0.7. That becomes the value of CE here, okay? So CE is no longer 0.68. It's actually 0.7 because that's the minimum value I should be using. Now, of course, these are exactly the same as we had in the other problem, okay? Now look how much simpler the table becomes, okay? So in other words, I have the same surfaces, I have the same importance factor, I have the same Q value, except now the CE value goes from 0 all the way to 10.9. So therefore, I only have one CE value. The CG values are exactly the same that I used for the other problem. And now, of course, my pressures are going to be a little bit smaller, but they're going to be from 0 all the way to 10.9 meters. So that's what the terrains can have an effect on your calculations, okay? And the same thing would happen for case number 2. The same CE value applies, in other words, 0.7. And of course, this is where we go and get, okay? So here I have the IS, I have the Q, and of course I only have one CE value because I have the same value across the whole height of the building. And these are exactly the same values that I got from here as I used in the other problem. These don't change. And now I simply redo my calculations, and you'll see that if you wanted to compare like one diagram to the other, that these would be a little bit less than what we got before. And of course, we went from 9 point whatever, and then these are a little bit smaller, therefore all these values here are a little bit smaller. And then once you've done that, we would do the same thing like we did before. We do our sketch, show the direction of the wind, go to, for example, so here you'll notice that I don't have an increase in wind pressure. It's uniform all the way across this wall, okay? And of course, again, okay, so in other words, points, so in other words, here's 1, 2, 3, and 4, negative, negative, positive, positive. So, you know, positive, positive, negative, negative, and here's the numerical value of the pressures acting on surface 1, surface 2, surface 3, surface 4. And of course, if on for the edge pressures, the one along the edge of the building or at the corners, they call it E for edge, I guess. You have the same directions, those don't change, but the numerical values are slightly higher than in the middle of the wall, okay? And that's how you would indicate that. And of course, now you've done the ones for the ones generally load case number A, and you would do the same thing for load case number B. Now the difference B is that these are all negative. Okay, so all the walls that are parallel to the wind direction, these are all negative, therefore they're all blowing away from the surfaces, and these are the values that you calculated in your table. You simply go back and look at, so I'm sorry, yeah, so in other words, you get the value for 1, for 2, see, they're all negative, for 3, and for 4, they're all negative. And then after that, you do the same thing for, and then these are, of course, the directions would be all the same, but the numerical values change at the edges. And then now here you would show a wind direction, because here you have a 5 is on the windward side and 6 is on the leeward side. Therefore, you have to show the direction of the wind, and I expect you to show me that. And here you show it as a pressure. And of course, if we go back, Okay, 5 is positive, is a pressure. 6 is negative, is a suction. And that's how I know whether it's a pressure or suction. And I do the same thing for 6 and 6E. Okay, so that could get that just to give you a little bit of appreciation how the terrain can have an impact on your on the values of your loads. Okay, and guys, if you are in doubt whether I should be using an open terrain or a rough terrain, without a doubt, be on the safe side. Always use the values of the open terrain. Okay, because then you're automatically going to be safe for a rough terrain. Is that clear? Okay, and that's the best way to do it. And I think, okay, so you're going to get an assignment, okay, and it's going to be due. It's going to be due like same as always, okay. And I appreciate you guys. Like I said, I don't know, is Mateus here today? I haven't seen him.
am.
Yeah, Mateus, why didn't you do your assignment last week?
I actually did not have time. I had to leave for something with my family like right after class. But it's okay. It was just like 5.
Mateus, like if you like, I want everybody, like you're the only one that didn't do the assignment, and I'm just
Yeah.
letting you know, because if all of a sudden I see that you guys are going to stop doing the assignments, I will then have the lab from 2 to 4. You'll all come and do the assignment during that. I mean, I don't mind, forcing you guys to come from 2 to 4 and making sure you're working on your assignment, because that's the time that we have for this course. Okay.
Yeah, no, I understand. It was
Okay.
just a special case, and I had to go. But today I'll do it.
Look,
And
I
I'll
have
do
a
it
special
every-
case. I have a special case. You send me an email, right? You send me an email saying I have a special case. This is what's happening. Believe me, I understand. I've had another student requesting this, and I understood what he's asking me for. And I told him, I said, well, do it and send it to me by Mayo. You understand?
Okay.
So if, for whatever reason, like for example, like if for whatever reason you can't do it, I expect you to, inform me the day before or the day of and tell me, sir, something happened today. I cannot do it today. Can you give me an extension? And if I think it's reasonable and that you're not doing this every week, I will give you an extension. Okay.
Okay.
But
Yeah.
I do expect everybody to do the assignment. Okay. And if I see that, like so far, you're the only one that didn't do the assignment, and
Yeah,
I'm
no, I understand.
okay. And like I said, and if I start seeing that, to me, the assignment is to reinforce what I'm doing here in the lecture. And then at the same time, by letting you guys do it on your own, because I can do 18 examples. And until you do your own, you won't see where you're going to be stumbling on your own. And then, like I said, if you have any, like, I don't expect the assignment to be correct. As long as I see that you gave it an honest effort to try to do it and you handed it in. And when I go over it, and if I see that you give it an honest, I'll give you the mark that you deserve for handing in the assignment. Okay. So Mateus, fair enough. And
Yeah. Yeah, no, I understand. It's okay.
Okay. So, okay. So that's, what time is it? Have we exhausted our time for today? Where are we now? Oh shit. I got a whole minute to spare with you guys. Aren't you happy? Okay. So this is what you guys are all waiting for, right? Okay. So guys, listen, like I said, I appreciate that you guys are working hard. Okay. And, don't be shy, guys. If there's something you don't understand, don't be shy to send me a Mayo. I will, if I can't answer your question, I will. And if I answer your question, if it's not clear, come back and say it's not clear, and then I will send you a link. We can have a Zoom meeting one-on-one, and I'm here to help you guys as much as I can. Okay. So if there's no more questions, I'm gonna stop this. I'm gonna stop the recording. Okay.